We are going to do section 1.6, other types of equations. We are going to cover 4 different equations in this section: rational equations, equations with radicals, equations with rational exponents, which these two are the same because a square root, for example, would be a 1/2 exponent. In this example right here, you have a rational exponent. 1/3 is the exponent, same thing as the cubed root, so these two are going to be quite similar process. And then equations in quadratic form, building on what we did in the previous 2 sections, learning how to solve quadratic equations. So a couple things to note is in these types of equations we are going to solve for proposed solutions, and those proposed solutions may or may not give a true statement back in the original solution. So just keep in mind, if we get in x value as an answer, that is a proposed solution, we are going to go back and check our work to see if it creates a true statement back in the original. So something that can be easily forgotten in different types of equations like this. Let's take a look at example number 1. So with a rational equation, the goal is to get a common denominator. Once we do that, we can just use the property that if you have a rational equation, and on both sides of the equation you have a common denominator, the numerators must also be equal. So we're going to find a common denominator. And then we're going to set the numerators equal to each other and solve for x. So in this particular example, we can notice that x squared minus x minus 2 factors as x minus 2 times x plus 1, and we're already kind of on the right track. So we want the denominator to be x squared minus x minus 2, and you don't necessarily need the least common denominator. That's going to be the most efficient. In this case we will get the LCD, which is x minus 2 times x plus 1. And I'll just factor on this side so everything looks exactly the same. Now, we can't change the statement from here to here. So if I'm going to write this expression, 3 over x minus 2, if I'm going to write that with the denominator of x minus 2 times x plus 1, I can't change the value of that expression, so I need to also have the numerator multiplied by x plus 1. And if you wanted to take a step backwards, you could cross this out, and you'd be equivalent to 3 over x minus 2. So that's the goal. We can't change the value of the expression. Over here, we originally had 1 over x plus 1. We want to write that with the denominator of x minus 2 times x plus 1. So in order to not change the value of that expression, we must multiply this expression's numerator by x minus 2. On the right-hand side of this equation, we don't need to manipulate it at all because we already have the common denominator. So here's where I'm going to note that x cannot equal 2 or -1 because those values would cause division by 0, and 2 and -1 are not in the domain, and we'll talk more about domain when we introduce functions. So if we go through all of this and we get either of these values as a proposed solution, we have to throw them out. Now the property that if each rational expression in the equation has the same denominator, the numerators must be equal. So on the left-hand side of this equation, we have 3 times the quantity x plus 1 plus 1 times the quantity x minus 2, and that has to equal 3. So from here, let's always pay attention to detail. And we're just solving as usual here. And we get the value of x equals 1/2. If we go back and substitute this into the original, we do get a true statement. And this value of x equals 1/2 does not cause division by 0. X equals 1/2 is in the domain. So I'll let the viewer do the calculator work here, but in order to show the proposed solution is correct, and if we're using set notation, then we would have 1/2 inside of the curly brackets. Okay, let's take a look at the second example, which was an equation with a radical. This example has 2 terms with a radical, and at a certain point in this example, I'm going to stop and say, if the original problem only had 1 expression with a radical, this is how you would go about solving it. So if we can do this one, we can do problems with just a single radical. So we're going to isolate one of those radicals on one side, and let's just do that by adding root x plus 1, and that'll isolate the square root of 2x plus 3 on the left. Okay, the reason we did that is now we can clear that radical on the left by squaring both sides. On the right, the radical term, we're still going to have a radical term after we square. So remember how to multiply this out. We're going to have 1 plus 2 square roots of x plus 1, and then once we square root x plus 1 times root x plus 1, okay, then let's collect some like terms and isolate the remaining radicals. So if you were given a problem that just had a single radical, you would start from this step. So we're going to isolate this radical. And if you wanted to here, you could divide both sides by 2, but we're going to square both sides, so having the 2 in front of the radical doesn't cause us any more difficulty. So if I square the left, I have x squared plus 2x plus 1. And if I square the right, 2 times 2 is 4, and then the square of a square root is the expression underneath the radical. Now this looks like we're going to end up with a quadratic equation, so we want ax squared plus bx plus c. Just like normal solving a quadratic equation, now we have to solve this quadratic equation from here, get the proposed solutions, and then go back to the original and see if those proposed solutions do indeed give us a true statement, the original. So I think that we are not going to have any quadratic formula involved here. It looks like we can just use the zero factor property, and x squared minus 2x minus 3 factors into x minus 3 times x plus 1. So the proposed solutions are x equals 3 and negative 1. And just to save time on the video, just like last time, I'll let you guys do the calculator work to verify for both of them. And this is when we check x equals 3. This is going to give a true statement. Then when we check x equals negative 1, plug that back into the original. This does also give us a true statement. So the solution set in set notation is 3 comma negative 1 in the curly brackets, or just x equals 3 comma negative 1. Now if we have an equation with a rational exponent rather than just a rational exponent that is something other than 1/2, you know, like the last one, square root can be written as 1/2 exponent. We're just going to raise both sides of the equation to the necessary power to clear that fractional exponent. So this example, we have a 1/3 exponent on both sides. So the first step would be to cube both sides. 1/3 to the third power is 1. The 1/3 power to the third power gives us, you know, to the first power, the property of exponents is if you have an exponent raised to an exponent, you would multiply them, so 1/3 times 3. Same thing on the right hand side. One thing to mention about this is in the original, with the 1/3 exponent, there are no domain errors. So like, it's a cubed root, it's okay to have a negative under a cubed root, or you know, something like that. So if we get negative solutions, unlike if it were a square root, you can't have a negative under a square root. That's a domain error. Just side note that cubed root, negatives under a cubed root are okay. That does not cause a domain error. So looks like we have a quadratic equation again. So let's get ax squared plus bx plus c. equals 0. And the checklist for solving a quadratic equation is always, try to use the zero factor property first and factor it. If that doesn't work, excuse me, maybe go to the quadratic formula. 4x squared minus 5x plus 1 does actually factor into 4x minus 1 times x minus 1. And if you need to pause the video and go off to the side and factor that, go ahead and do that. So on this one, the proposed solutions are going to be the solutions because we don't have domain errors anywhere. So x equals 1/4 and x equals 1. Solving from here. And if we go back and check, we do verify that 1/4 and 1 do both work. Still go back and check, even though in this particular example, if you had something to like the 5/4 power or something like that, you could have domain errors. So still go back and check. And the last example, we're going to do what's called an equation in quadratic form. You just notice the pattern of ax squared plus bx plus c, and then we can substitute using something to the second power and then solve from there. So we notice that x to the 4th is a quantity squared. So when you're solving equations in quadratic form, that's what you're looking for. You're looking for that quantity squared. So in this case, A equals 1, B equals 0, and C equals negative 100. If we notice that x to the 4th is x squared squared, we can pick something else. I'm just going to say let t equal x squared. That would mean t squared minus 100 equals 0. And we are looking at a quadratic equation exactly as it would have appeared in the previous section. Solve it as you would. So this is a difference of squares. So t plus 10 times t minus 10 equals 0. So t equals plus or minus 10. Now, t was substituted for x squared. So x squared equals 10 or x squared equals negative 10. So over here on this side, we square root both sides. We get x equals plus or minus root 10. Over here, we cannot take the square root of negative 10. So this x squared equals negative 10 does not provide any real solutions to the original problem. And if you recall back from 1.3, we would need the imaginary unit in there to end up with something like the square root of negative 10. Root 10i, if it were a solution, we'd end up with that. So over here, x equals we propose the solution of root 10 and negative root 10. Let's go back and check. Root 10 to the 4th power minus 100, does it equal 0? So root 10 squared is 10, and then 10 squared is 100. 100 minus 100 is 0, so that is true. And we're going to end up with the same outcome, a true statement, if negative root 10 to the 4th is substituted for x. So negative root 10 to the fourth minus 100. Does it equal 0? That is a true statement. So our solutions are root 10, comma, negative root 10.